All right, let's kick off our discussion of Chapter 9 on liquids and solids. And if we're thinking about the physical properties of liquids and solids, we need to define intermolecular forces. As the inter prefix reveals, this phrase refers to forces that exist between molecules. In fact, they are forces that attract molecules to each other. So intermolecular forces are what hold molecules together in liquid or solid form. And liquids and solids, unlike gases, are condensed phases. So compared with gases, liquids and solids are going to have stronger intermolecular forces. And since solids are more condensed than liquids, solids are going to have, on a relative scale, stronger intermolecular forces than liquids. That's what holds the molecules together in the condensed phase. Okay, it can be molecules or particles, but we'll talk more about that in just a moment. There are three types of intermolecular forces, and I'm going to go through them in order of weakest to strongest. So this is the weakest type of intermolecular force. IMF is going to be intermolecular force. The weakest type of intermolecular force is the London dispersion forces. These have lots of different names. Sometimes you'll hear them referred to as just London forces or just dispersion forces. Another name for them is the van der Waals forces, named after the Dutch scientist. So sometimes you'll hear them referred to as van der Waals forces. These are ubiquitous, meaning that they are present in absolutely all molecules. All you need to have is electrons. So they're present in all molecules. And they arise because of what we call instantaneous polarization of bonds. Sometimes you'll hear that instantaneous polarization of bonds referred to as induced dipoles. And I'll define what induced dipoles are in just a moment. The London dispersion forces, although they are ubiquitous, although they are present in all molecules, they really are only significant in nonpolar molecules, molecules with no dipole. So examples of nonpolar molecules would be small homonuclear diatomics like nitrogen or hydrogen, any kind of hydrocarbons. Okay, so hydrocarbons are compounds in which you have only carbon and hydrogen. So CH4, for example, doesn't matter how big it is. It could be a really big one like C8H18. Any molecule where carbon and hydrogen are the only two elements present is going to be nonpolar because carbon and hydrogen have very similar electronegativities. Okay, so nonpolar molecules have no dipole, no dipole moment. There's typically no difference in electronegativity among the atoms, or those differences cancel each other out. And these kinds of nonpolar compounds tend to have pretty low boiling points because dispersion forces are relatively weak. They're the weakest of the intermolecular forces. So let's talk about induced dipoles, or instantaneous polarization, and what gives rise to these dispersion forces. Let's take the simplest molecule we can, the hydrogen molecule, H2. So in H2, we have two hydrogens bonded to each other. I'm going to draw two H2 molecules side by side. So these are two H2 molecules side by side. So they're nonpolar molecules. Hydrogen has the same electronegativity as hydrogen, so there's no bond dipole there. However, as the electron moves around the nucleus in hydrogen, there are going to be momentary asymmetrical charge distributions around the nucleus. And what that does is it gives the atom just a momentary instantaneous dipole. So let me explain that one more time. Hydrogen has a proton in the nucleus and electrons, one electron going around the nucleus, right? So let's say at any given moment, you have more electrons on this side of the molecule. That's going to give this side a partial negative charge. That's my symbol for the partial negative charge, leaving this side with a partial positive charge. That's what we call an instantaneous dipole, and it can just happen for a moment. Instantaneous dipole. However, it has an effect because then the molecule next door is going to be attracted, the electrons in it are going to be attracted to the positive end of that molecule. So you're going to have the electrons move to that side, and that's going to leave the opposite side with a positive charge. So the instantaneous dipole goes on to induces a dipole in the molecule next door, in the neighbor molecule, and that will happen again and again and again and again, and so on and so on and so on. So you have these very small instantaneous dipoles on molecules. And those momentary asymmetrical charge distributions are strong enough to attract molecules to each other. So, one kind of interesting question that I can ask you is, what do you think? Are these dispersion forces, these London dispersion forces, greater for large molecules or small molecules? So are these dispersion forces greater or stronger for larger or smaller molecules? Think about that for a moment. Well, London dispersion forces depend on electron distribution being asymmetrical. And larger molecules are going to have more electrons in them, right? Larger molecules, more atoms, more electrons. The more electrons you have, the more likely they're going to exist in an asymmetrical charge distribution. So the more likely they're going to be polarizable. So larger molecules, because they have more electrons, are more polarizable. So for London forces, larger molecules are going to in general have the stronger stronger London dispersion forces. So larger molecules are more polarizable simply because they have more electrons and more possibility for instantaneous dipoles. Okay, so you're going to have London dispersion forces being greater. I'm going to call them LDF, London dispersion forces, are stronger than they are for small molecules. Okay, now let's move on to the second type of intermolecular force that can exist between molecules. The second type of intermolecular force is the dipole-dipole interaction. And this is important for polar molecules. So dipole-dipole interactions are much stronger, much stronger than London dispersion forces. And they arise from electrostatic attraction between polar molecules. So London forces are really negligible in magnitude compared with dipole-dipole interactions. Dipole-dipole interactions give rise to much higher boiling points, and they change a whole host of other properties that we're going to talk about later in this chapter. Let's take an example of a polar molecule. Let's take HBr. So HBr, let's think about molecular gas phase HBr. HBr is a very polar molecule. Bromine is a halogen. Halogens are very electronegative. So we have the partial negative charge on the electronegative halogen and a partial positive charge on the electropositive hydrogen. And we have a bond dipole and an overall dipole moment in this molecule. So it's very, very polar. And what happens is it's kind of analogous to what I just explained for the instantaneous dipoles, except these are permanent dipoles. Okay, this is a permanent bond dipole rather than an instantaneous one. And that means that it's stronger. So this is going to have this similar effect on the molecule next door. The molecule next door is going to orient itself so that its electropositive atom is near the electronegative atom on its neighbor. So the molecules orient themselves to maximize the attraction between opposite charges and minimize the repulsion of like charges. Okay, so the permanent dipole means that molecules orient themselves, position themselves to maximize the attraction of opposite charges. That's called electrostatic attraction. The attraction of opposite charges is called electrostatic attraction. So, one truth that is very important is this. The greater the dipole, okay, the more polar the molecule, the greater the difference in relative partial charges. And the greater the intermolecular forces, the stronger the intermolecular forces. So another way of saying that is the more polar the molecule, the stronger the intermolecular forces are going to be. So more polar molecules are going to have higher boiling points because they're going to have stronger intermolecular forces holding the molecules together as a liquid, and they don't want to be released into the gas phase. So the more polar the molecule, the stronger the intermolecular forces. The third type of intermolecular force, and this is the final type of intermolecular force, is the hydrogen bonds. Hydrogen bonds really are just a special case of dipole-dipole interactions. They're not really bonds, so this bonds is a misnomer. They are not really bonds in the way that covalent and ionic bonds are bonds that hold atoms together. They're really just a super strong type of intermolecular force. And the reason they're called hydrogen bonds is because they're so strong that sometimes they can be as powerful as bonds in holding certain molecules together. Hydrogen bonds occur in polar molecules where hydrogen is directly bonded to F, N, or O. Let me give you some examples. The HF molecule, hydrogen's directly bonded to fluorine, that would show hydrogen bonding. Water, H2O, hydrogen directly bonded to oxygen. This would show hydrogen bonding. Ammonia, NH3, hydrogen is directly bonded to nitrogen. That molecule would show hydrogen bonding. So the reason for this is that fluorine, oxygen, and nitrogen are extremely electronegative. And what happens is that in that bond, because of the extreme electronegativity of fluorine, for example, hydrogen's share of the electron pair in the bond is so small that hydrogen essentially appears as an isolated H plus ion. And as a consequence, it is very attracted to electron pairs in other molecules. This is the root of hydrogen bonding, and we know that water engages in hydrogen bonds. So, for example, looking at water, this hydrogen in water is really searching for electron density. So it kind of looks to the oxygen in the molecule next door to get what it needs electronically. Okay, so a hydrogen bond occurs because the hydrogen is so deprived of electron density from its bond with oxygen that it's going to look to the oxygen in the molecule next door to get some electron density, okay? Being bonded to such an electronegative atom leaves the hydrogen atom really hungry for electrons. So you get these super long, extensive hydrogen bonding networks. And that's what gives water all of its kind of interesting physical properties like surface tension and high boiling point and that kind of stuff. So this explains high boiling points of compounds like ammonia and water and HF. Okay, the stronger the intermolecular forces, the higher the boiling point is going to be because the molecules are more attracted to each other. They don't want to vaporize. So hydrogen bonding is the strongest type of intermolecular force. It's not as strong as a true bond, like an ionic bond or a covalent bond, but it's the strongest type of intermolecular force. So to summarize what we've learned in this lecture, the London dispersion forces are going to be the weakest by far of all of the intermolecular forces. So those are much weaker than the dipole-dipole forces. And the dipole forces are weaker than hydrogen bonds, but really hydrogen bonds are just a special type of intermolecular force. So one thing that's very important to note is that if a molecule has more than one intermolecular force at play, it's going to be the strongest intermolecular force that dominates. So, what that means is that London dispersion forces are only going to be important and dominant for nonpolar molecules. Dipole-dipole forces are going to be dominant for polar molecules, except for molecules where H is bonded to F, N, or O. And in those cases, we're going to have the extreme example of hydrogen bonding. So all these various types of intermolecular forces are what account for the variety of physical properties that we see in liquids.